All right, guys. Well, let's finish up numerical differentiation. We're in section 4.2 now. Okay. Very short lesson. This will be like a Thursday lesson when we have a quiz, which is going to be Richardson extrapolation. Okay. Now, there's quite a bit of theory with Richardson extrapolation, but we're not going to go into all that. If you're interested, the book talks about it in quite a bit of depth. But let's just kind of look at the method and how to apply. So the topic for the day, our only topic for the day is Richardson extrapolation. So Richardson extrapolation is a method that uses a weighted average of previous approximations to refine an approximation of f prime of x. Now, the idea of Richardson extrapolation can actually be extrapolated, to second derivatives and third derivatives and things like that. But we're going to keep it to first derivative. Okay. So let's just talk about the Richardson extrapolation algorithm. So what we going to do is we will define kind of these new functions or new equations. So we're going to define n sub 1h, to be equal to, in this case, we're going to use our midpoint difference formula, f of x plus h minus f of x minus h over 2h. We know that this midpoint formula has error of big O of h squared. Okay. Big O of h squared. And it can be proven. Where can it be proven? In the book. I don't think you guys want me to go through all of these proofs. Some of you guys are interested in these proofs, but to go through all these proofs would take quite a bit of time. Can be proven that n sub 2h, which is equal to, let me put n sub 2h over here because it's big, n sub 2h, which is equal to n sub 1 at h divided by 2 plus 1/3 of the quantity n sub 1 evaluated at h divided by 2 minus n sub 1 of h has error of big O of h to the 4th. Okay, so essentially we go from h squared to h to the 4th by using this weighted average. Notice that this is a weighted average where we're taking essentially averaging this approximation at for different values of h. Here I'm dividing h by 2. Here I'm using h, my original value of h. And I'm just kind of averaging the approximations when I use h versus h divided by 2, right? And I'm saying that this approximation, I know n sub 2h is going to have error of big O of h to the 4th, which is better than what we start out with. And n sub 3h equal to n sub 2h, n sub 2h divided by 2, plus 1 divided by 15 times n sub 2 h divided by 2 minus n sub 2 h has error of h to the 6. So guess what? Now we have an even better approximation than we had before. And we can go on to n sub 4 and n sub 5 and so on. And I'm going to give you guys a general formula in just a second. But let's do an example to kind of get our minds wrapped around this idea. Okay. So here's my example. Why not look at e to the x? So let f of x equal e to the x. X equals 0. H equal to, you think it's going to be 0.1? No, it's going to be 1. And we wish to approximate. F prime 0. So we wish to approximate f prime 0. So let f of x equal e to the x equals 0, h equal 1. We wish to approximate f prime 0. And I'm going to use Richardson extrapolation. And we're going to approximate it down to n sub 3h. That's what we're going to do. So n sub 1, my h is, in this case, 1. So n sub 1 is going to be equal to f of 0 plus 1, right? So that's going to be f of 1 minus f of 0 minus 1. That's going to be f of negative 1. All that divided by 2. It's going to be e to the 1 minus e to the negative 1 divided by 2. When I do that, I get my answer to be 1.1752. Not a great approximation, by the way. Not a super astounding approximation. Now let's take a weighted average of n sub 1, right, at different values of h. Okay. So n sub 2h is going to be our weighted average of n sub 1. So n sub 2h, so my h is 1. That's going to be the same thing as n sub 1 h divided by 2, which is going to be 0.5. Plus 1/3 of n sub 1 at 0.5 minus n sub 1 at 1. Guess what? We need to figure out what n sub 1 of 0.5 is. So let's do that over here. N sub 1 of 0.5, right? It should be very similar to what we just got doing. It's going to be e to the 0.5, right? Minus e to the negative 0.5 all over 1 this time, because 2 times 0.5. N sub 1 to the 0.5 I have is 1.0422, and I'm rounding. So let me plug in and see what I get. I get 1.0422 plus 1/3, 1.0422 minus 1.1752. And when I work this out, using 4 decimal places, I get 0.9979. That's a better approximation for sure than what I had before, right? Using this weighted average. I'm like, okay, that's pretty neat. Well, can I get better than this, right? Can I get a better approximation than this one? Well, we can try by taking a weighted average of n sub 2. So if we use our formula that we have here, right? For n sub 3. So n sub 3 of 1, that's going to be equal to n sub 2 of 0.5 plus 1 over 15. 1 over 15 times n sub 2, 0.5 minus Now I know some of you guys are already trying to figure out a pattern, right? You see 1/3, you see 1/15, right? It seems like everything else stays about the same, right? We're changing our subscripts, but we're going from 1/3 to 1/15. Then you think, so that's got to be a pattern here, right? There's got to be some kind of a way of looking at this problem. And there is, right? There is. So let's plug in and see what we get when we do this one. Plugging in, right? So what do we have? Oh, do I know it's a 2 of 0.5? I don't, right? So let's find out what that is. Okay, so 2 of 0.5. Right. And what do we get when we do that? That's going to be, well, we need to do a lot of work to be able to figure out instance 2 of 0.5, right? That instance 2 of 0.5 is really instance 1 of 0.25. Oh my goodness. Plus 1/3 of instance. I need more space. Let me just go over it a little bit. This thing is more work than I thought it was. Kind of reminds me of the difference, divided difference formula. Instead of 2 of 0.5 is really equal to instead of 1, right? Of 0.25 plus 1/3 of instead of 1 at 0.25 minus instead of 1 at 0.5. So really, I need to figure out what instance 1 of 0.25 is, and I know what instance 1 of 0.5 is. I just did it up there. So the only new one I'm looking for is 1 of 0.25. So instance 1 of 0.25. This is equal to e to the 0.25, right? Minus e to the negative 0.25. All that divided by 2 times 0.25, that's going to be 0.5. For that, I get 1.0104. 1.10104. So let's plug that in. Instance 2 at 0.5 is equal to 1.0104 plus 1/3 of 1.0104 minus 1.0422. And what do I get for instance 2 at 0.5? I have 0.998. 998. This is not even what I'm trying to solve for. But I need this to be able to plug it in here. So I get 0.9998 plus 1/15 times 0.9998 minus instance 2(1). Where was that guy again? Oh, here it is. 0.9979. And when you work this out, what I have is 0.9999. I just went to 4 decimal places. Here. That's pretty neat, right? So I use kind of this succession of approximations to get my best approximation, right? Which is this guy here. My best approximation, 0.9999, is what I wanted to get, right? By using kind of a series of other approximations. Now I noticed that my H started at H equal to 1, right? But I did have to evaluate it at 0.5 and 0.25, right? But even if you evaluate at 0.5 and 0.25, your approximation is not going to be anywhere as good as this. Right? And you can try it out for yourself. Do the midpoint formula using h of 0.5, and do the midpoint formula using h of 0.25. Right? Which actually we have it right here. Here's the midpoint formula h of 0.5, right? 1.0422. Here's the midpoint formula h of 0.25, right? 1.0104. These are not bad approximations, but this one is way better, right? And actually, if I had shown more decimal places, you would have seen a lot of the accuracy of this as well. And so, Richardson extrapolation is good when we want a good approximation. I know I used good twice. Without using a very small h. Right? So I know I have to do more computations, right? But suppose that for whatever reason you can't go back and get smaller values of h. And that can occur when you have a function. You have a function, and maybe the function is very labor intensive to be able to get lots of points for, right? Very close together. Or you don't have any more data that you can use, right? You only have this many points, and you have to get as much accuracy as you can for the derivative using the points that you have, right? And so Richardson extrapolation allows you to do that with whatever. So I suppose you only have your points to a width of 0.25, right? You don't have your points are not 0.1 from each other or 0.01 from each other. The smallest value, the distance between your points is 0.25. And so Richardson extrapolation is good. It gives you a good approximation of the derivative. So in general, we have that for Richardson extrapolation. We have that n sub 1h. Like we said before, it's going to be given by f of x plus h minus f of x minus h over 2h. And I can say that n sub k plus 1, n sub k plus 1 of h is equal to n sub k of h divided by 2 of h divided by 2 plus 1 divided by 4 to the k minus 4 to the k minus 1, 4 to the k minus 1 times n sub k evaluated at h divided by 2 minus n sub k evaluated at h for k greater than or equal to 1. So let me say this again. N sub 1h is just going to be our divided difference formula. N sub k plus 1, right? So if k is equal to 1, this becomes n sub 2h is equal to n sub 2h divided by 2. 1 divided by 4 to the first power, right? Because k is equal to 1. So that'd be 4 minus 1, which is 3. N sub 1, h divided by 2. minus n sub 1h. If k is equal to 2, right? If k is equal to 2, this becomes 2 plus 1, so this becomes n sub 3. So n sub 3h equals n sub 2, h divided by 2, plus 1 divided by 4 to the second power, which is 16 minus 1, so I get 1 divided by 15, n sub 2, h divided by 2 minus n sub 2h, right? So this is our formula for Richardson extrapolation. Now there is a nice tabular form. There's a nice tabular form for Richardson extrapolation that I want to put down. Tabular form. Okay. This is also in the book. It's good to have it here. Here I have my values of k. 1, 2, 3, and 4, for instance. And let me just talk about, this is the error, right? I'm going to have a column for the error. So I'm going to look at all of the extrapolations that are big O of h squared. These are all the extrapolations that are big O of h to the 4th. These are all the extrapolations, the n sub 1 terms that are big O of h to the 6th. And this is the one that are big O of h to the 8. So just going down, what are going to be the extrapolations that are big O of h squared? That's going to be n sub 1 h, n sub 1 h divided by 2, n sub 1 h divided by 4, and then n sub 1 h divided by 8. Of course, I can let k keep continuing, right? So k can be 5, 6, 7, right? So this is going to be h divided by 2, h divided by 4, h divided by 8, h divided by, what would that be, 16, right? H divided by 32, so you divide every time you divide it by 2, you're dividing h by 2 in every step. To get big O of h to the 4th, these terms here, right, I have to use the previous terms. I'm going to have to be able to get big O of h to the 4th, and n sub 2h will be here. And n sub 2h requires n sub 1h divided by 2 and n sub 1. It requires these two terms right here. N sub 2h divided by 2 also requires two terms, but it requires the middle terms, these two guys right here. And n sub 2h divided by 4 requires the last two terms. Big O of h to the 6th, right? When we look at this one, this is going to be n sub 3h. And n sub 3h requires these two terms to the left of big O h to the 4th. N sub 3h divided by 2 requires the last two terms here. These last two terms. And then finally, n sub 4h. N sub 4h requires the last two terms of the big O h to the 6th column. Right. And of course, you can extend this out to k to 5, 6, however many terms you want. The next one would be big O of h to the 10, then big O of h to the 12, big O of h to the so on. Okay. So let me just kind of show you guys how our formula would look in that tabular form. What would you do in practice when you're trying to solve this? What would you do in practice? Remember what we had before. Again, I had f of x is equal to e to the x equals 0, h is equal to 1. and we went out just, if we were to do the tabular form, we went to n sub 3, right? So k would go from 1, 2, and 3. 1, 2, and 3. 3 times 2 is 6. So that means we're just going to have the first 3 columns here. Big O h squared, big O h to the 4, big O h to the 6. Okay. And so what we'll be looking at is we will have essentially this. We have n sub 1, 1, n sub 1, 0.5, and n sub 1, 0.25, right? This is what we have in the first column. And what I would do in practice is I would find out what these values are first, right, in that first column. And we already did that, so I'm not going to go through that again. But I will create another table where we have the stuff evaluated. So at k equal 1, 2, and 3, what we got was 1.1752, 1.0422, 1.0104. Right? Once you have these values, right, it's easy to get the other ones. We just have to remember what form my n sub k plus 1 is in for that particular row, for that particular column. So this is big O of h to the 4th, right? And this is big O of h to the 6th. Let me continue filling this out. This will be, going by what we have there, this will be n sub 2, 1. This will be n sub 2, 0.5. And this will be n sub 3, 1. Right? But once we have this column, right, all thing we have to do is just remember how this is set up. And I'll actually do this on the side, right? So once we have this first column, n sub 2, 1, I know to get this row entry, then I need to take this guy. Actually, I need to take this guy, 1.0422, right? Plus 1 over, it's going to be 4 squared, 4 minus 1, times, in this case, I have 1.0422 minus 1.1752. So I take this plus 1/3, which is the same thing that we have there, k equal to 1, okay, of this minus this. So this is kind of my weighted average that I'm adding to this, right, to get a better approximation. And what I get when I do this, again, is 0.9979, I believe is what I put down last time. And to get this term right here, it's a 2 of 0.5. I do the same thing, right? I'm going to have the same weight. So the only thing I'm doing is changing numbers. So I'm going to have 1.0104 plus 1 over 4 minus 1, which is 3, times 1.0104 minus 1.0422. And we know that that is equal to 0.999. And finally, to get the last one, right, n sub 3, 1, is going to be this term, 0.9998 plus 1 over 4 squared minus 1, or 15, times 0.9998 minus 0.979. And we know that that is going to work out to be 0.999. So what you have to do it's really, you just have to remember what is your original formula, right? What's your original derivative? So if this was a second derivative, it would work the same way. We just use a second derivative formula, right? Or we can use a different first derivative formula if we wanted to, and use Richardson extrapolation, right? But whatever the case is, you have your original formula for the derivative that goes into the first column, right? And you continually divide by 2 in each row. So the next row is divided by 2 in terms of the h, and so forth. Find those values, and once you have those values in the first column, then just use this formula, right, to be able to get the other values based on what the values in the first column. And once you have the values in the second column, use those values to get the values in the third column. And if you have a fourth column, use those values in the third column, get the values of the third column, get the values in the fourth column. You keep doing that over and over and over again until you refine your derivative to wherever you want it to be. Okay, so this is the idea, this is the concept behind Richardson extrapolation. All right, so we'll stop there and we'll pick up with numerical integration.